Hello, everybody. I hope you guys can hear me. So welcome to the 2020 summer internship here at WinLab. As, of course, everybody else is struggling with the COVID stuff, we had to do our internship this year over the remotely, right? And so this is now our open house. We have quite an interesting number of people already on the call, and hopefully more will join us. But without further ado, let's start. So who's going to be the first? We did have a schedule. So I believe the first group is the social distancing group, right?
Oh, can you hear me, Professor?
Yes, go ahead, Emmanuel.
Awesome. Let me just share my screen. My browser saying it's preventing me from sharing my screen. I guess someone else should go first. Let me see if I could change my browser real quick.
Okay, sure. So let's go for the second talk, which is UWB, if you guys are ready.
I think our other teammate is having some problem with the audio.
So,
He's not able to hear.
Yeah, welcome to the online world, right? Yeah.
Actually, we changed from Meet to Zoom, so I think he has some configuration issues.
Okay, yeah, sure. No, the whole idea with Zoom is that it's a little bit more friendly for the larger crowd and for quick switching of participants, right? So
sorry for the inconvenience. We could go next.
Okay, so let's see. How about if you go for the third talk, if you guys are ready?
Oh, Professor, I actually just got I'm the social distancing group. I actually
go ahead. Go ahead.
Wonderful. Let me share my screen real quick.
Yep. Go for it.
Okay, can you see everything okay?
Yeah, you're good to go. Start, please.
Okay, so my name is Emmanuel Maljurovic. I'm a part of the social distance, analyzing social distancing based on sensory inputs group. My partner is Kuhu Haldir. She fortunately wasn't able to attend this presentation. We were supervised by Professor Jorge Ortiz and advised by Murtada Oldir. So COVID-19 has had a tremendous impact on current day society and the new precautions that we have to take to ensure day-to-day safety. The objective of our project was to use object detection to gauge social distancing policies on a population in an urban setting. So we're going to be specifically focusing on detecting whether people have masks or whether people are within 6 feet apart of each other, or in other words, just adhering to social distancing. We're hoping that we can create a map on urban mobility and space occupancy in a major city, and then eventually infer different activities and the context of people and understand how they're moving in urban populations, and then address questions on the effectiveness on social distancing. Now, quick little pipeline on the project. The first step was to upload some of the data, which comes from the New York City Department of Transportation. So it's just footage. But however, where the footage is coming from is sort of irrelevant. It's more about, is the footage viable? And then we're going to use object detection through YOLO, which I'm going to talk about in a second, to see, is a person being detected? And if so, are there other humans around that person? And if that question is also answered yes, then what's the distance between those people, and are they wearing masks? And we hope to collect and organize this data to hopefully draw some conclusions about social distancing. So what is YOLO? YOLO is a framework that uses deep learning neural networks for object detection. What it does is it applies a neural network on a photo, and it separates that photo into different regions depending on whether it detects an object or not. So for example, hopefully you guys can see my cursor. You can see it detects multiple people, it detects a bicycle car, and it puts kind of like a bounding box around them to signify, that's what we believe it is, that whatever that object is. And it also, which you're going to see in a second, provides probabilities of how confident how confident the accuracy is on determining what type of object it is, whether it's a person, a truck, or anything. So how are we using YOLO? We're using YOLO on thousands of these pictures, or in other words, the data that we were able to extract from the New York City Department of Transportation. And this is a really good example where for this image and analyzing it produced, it was 49% sure that whatever that person, that photo was a person. Or for example, it's 28% sure that whatever car that was a car. And it's able to do this for every object in every photo. And, with this data, we can sort of analyze this and then, start to count the objects, which we were actually able to produce. We were able to graph an output and we were able to separate it between the days and, count the amount of cars, trucks, or people on that given day, which could be really useful for us because, we could use this graph to compare on pre-COVID data to see, are there more people walking in the streets, or are there more cars or more, vehicles on the streets, which may suggest that there's more traveling or there's more people moving around. So it can give us some interesting, or can help us make a conclusion of, is social distancing being, adhered to? And then we were also able to produce this output, and there's four, elements I want to talk about, which one, it takes into account the place, which as you can see with this map, it gives you the address of it, but it's also, the geolocation data, where is it a residential area? Is it a commercial area? What's the socioeconomic status of that area? And once we can, if we're able to gather data from that area and then draw conclusions, we can kind of maybe relate to, does it have to do with maybe the socioeconomics or perhaps where that's located in the city? And then it comes down to the people themselves, which, are they wearing a mask? Which, as you can see, the program detected, this is a person, there's a bounding box outside of them. It also detects if they're wearing a mask or not. And it also tells you, is the person a male or is it a female, or what age is that person, which could also be interesting, seeing, what's the typical age for, if there's a lot of, people walking around at this time, what's the, average age of that group. It also addresses the distance between the actual people. So you could see, I guess this person, there's 10 feet apart from them, 12 feet apart from these people. So that could also really help us understand that, are these people clustered in one spot, or are they more or less separated, following these social distancing policies? And also, what exactly are these people doing? These people are both walking, but, this guy has a shopping bag that perhaps may indicate, he was at a shopping store in a very highly populated area. If more people, or if you're sitting down in a coffee shop, you could be at risk for, a COVID, since you're in an enclosed space. So, once we're able to run this on thousands and thousands of images, we can gather that data and then, make conclusions from it. So our future aspirations is to use all of the data that we've collected and start to analyze it and start asking questions, or when and where is this happening, in what areas of New York, and at what times in New York are these people congregating. It could also give us interesting data on like small scale human interaction. Are most interactions, is there 5 people or are there 30 people? That could also give us some insight on how Corona is spreading, and whether it's spreading at the same rates in certain areas where there's small scale human interaction, or compared to other areas where there's larger scale human interaction. And then it could also be interesting for, well, sort of like I said before, the infection patterns, where we can actually compare infection patterns and the rate at which the virus is spreading between cities, depending on whether they're following social distancing or not. So, the future is to start asking these questions and then begin analyzing so we can answer them. And that is it. Does anybody have any questions?
Yeah, so please, everybody, feel free to ask questions at the end of every presentation, or you can also use the chat feature and pose the questions. And of course, I just added the link to the pages that describe each of these projects, and so feel free to reach out to these students even afterwards if you have some ideas. So if you don't have any questions, thank you very much. Let's go for the second.
Ivan.
Yeah. Yes.
Hi, Ivan. This is Dan. How are you?
Fine, thanks. How are you, Dan?
Do you think I can put a question or two?
Absolutely, please, by all means.
So really interesting work. The question that I have is, did you train the YOLO to detect masks, or you're using a model that you got already to detect masks?
We were actually already we found a lot of resources on GitHub, which, gave us a little bit of help on, the mask detection. So to answer your question, we didn't train them ourselves. We used a lot of resources to help us out with that.
Got it. And the other question I have is, what's your experience about resolving individuals, individual people in a crowd? In other words, using YOLO, you know that they use the bounding box to detect people. If you have a group of people, say 5 or 6, that you can inspect yourself and count them, right? And then you run YOLO, do you think that the number is accurate?
Well, it does give us YOLO what it believes its accuracy is for all those people. So like I showed you before here, let me share my screen real quick one more time. So I think you might be referring to this example where it kind of gives you the accuracy rate for each object detected. So we could actually set a threshold for, let's say, if there are 5 people and YOLO detects, I don't know, one of them is 50%, the other one is 60%. We can add a threshold and say, if it's above, I don't know, 45 or 50%, we're going to count that object.
Mm-hmm.
Or, NOB will count it. And if it's below 50%, we're going to, it's not conclusive enough. So we're going to ignore that.
Okay, but you haven't seen that you basically, YOLO is bunching up 2 or more people and saying, hey, here's a person with 70% accuracy.
I see what you're saying. No, I see what you're saying. We haven't had that error yet. It might be because, I guess, given the current circumstance, we really don't find people that are congregate like at a concert or something where there's a lot of people in one area.
Okay.
But it's going to be interesting trying to resolve that issue if we do happen to come across it.
Okay. Thank you very much.
Thank you. I appreciate it.
Thanks a lot. Okay, so if you don't have any more questions on the first project, let's go for the second one, which is the UWB. Are you guys ready?
Yeah, we are ready. We can go ahead.
Sure. Please go ahead. Grab the screen and go ahead.
Is my screen visible? Hi, everyone. Is my screen visible?
Yeah, it is
Yep,
visible.
you're good to go.
Yeah. Hi, everyone. So our project is Intelligent Ultra-Wideband Network. My name is Sayyam, and I am here with Amod. Our mentor is Karim Bona, and our advisor is Dr. Petra. So these are our email address, and feel free to contact us if you have any question regarding this presentation or our project. So what is our problem statement, or what we are working on, is to understand the basics of ultra wideband wireless communication and use that to simulate a clock synchronization in ultra wideband wireless sensor network. So what is ultra wideband? Ultra wideband is a fast, stable transmission of data indoors and outdoors, and it is not tied to any frequency. It does have an bandwidth regulation from FCC, which state that the bandwidth should be greater than either 500 megahertz or 20% of the arithmetic center frequency, whichever is lesser. And they also limit the power spectral density of these signals, which is limited to minus 41.25 dBm per megahertz. It can be widely used with many of IoT applications, such as in sports, in smart homes, in smart industries, and much more. So coming to clock and clock synchronization, what is clock and what we can do with clock synchronization? So clock, every sensor in a network has its own clock, and we can represent that with a time function, simple time function. Though these clock are, when they are initialized, they are perfect, or they can have an initial skew, but over the initial offset, but over the time they tend to deviate from their idle behavior, and they tend to develop an frequency skew. So what clock synchronization done is it provides a procedure of providing common notion of time across the distributed system, and this clock synchronization is very crucial for an intelligent or a self-aware wireless sensor network. So now Amod will explain the basic algorithm which we simulated for clock synchronization.
Yeah, to start with the clock synchronization, we chose Berkeley's algorithm, which is a basic implementation. And as you can see from the figure, Berkeley's algorithm is applicable for distributed networks. wherein a single master is communicating with different slaves. In this distributed network, the master requests for time from different slaves, and then the slaves communicate their own individual time, which would be different. And then the master calculates the time differences based on its own time, and then decides on a single time, and that is communicated to the rest of the slaves. And thus synchronization is achieved within the network. So this simulation we did in Python. So over here, you can see there are, on the master node, there are different clients which are connected, and the synchronization is happening at every slave node, wherein the slave is communicating its time, and then master is calculating a synchronized time for all the clients, and then it is being communicated to individual clients so that the synchronization is achieved. Next, we did was to simulate a MATLAB simulation for baseband, as in we were not able to do it for UWB frequencies because those range in gigahertz. So we tried our experimentations in baseband. And over here, you can see the block diagram of the transceiver which we used based on the root raised cosine filter. And we did a fixed delay computation at the receiver end. Over here, the channel was corrupted with additive white Gaussian noise to have the randomness. Moving next, we can see the different codes that we use for input into the system. Over here, you can see the random code wherein we selected the sequence ourselves as in 1, 1, -1. Then you can see the Barker sequence, which is a fixed length sequence. And these are usually chosen due to autocorrelation properties that they have. And that is how they are less likely to interfere with the other sequences. And the estimation on these sequences are very good. And similarly, the pseudo random noise sequence or the PN sequence also are deterministic codes, which have like a randomness property. And we try to compare these 3 different sequences in our simulation. So for the RRC filters, we were adding trailing zeros so that we do not have data loss. So additional to these symbol lengths, we were adding trailing zeros.
Now Amod has explained these 3 sequences on which we have worked on. Now I will explain how we have calculated the delay. So we have used the correlation property of these sequences to calculate the delay. So we calculated the correlation for the original waveform and the received waveform, and we calculated it for different SNR values. For example, for random sequence, we calculated the autocorrelation when there was no noise, that is SNR was infinite, and we can say that there is a distinct peak at -6, so that we can say that the signal is delayed by 6 milliseconds. The difference between all these sequences is that for Barker sequence and PN sequence, because of their autocorrelation property, the peak is way more profound than the random sequence, and the difference between first maxima and second maxima is clearly visible. But these all properties are distorted or deteriorated when we added noise to system, and we can see that for the SNR -20, even for such a small value, there is no distinct peak or there's way less difference. So from here we can conclude that the choice of code is relevant when we are doing a correlation, and it always helps us to have a better distinction between the first peak and second peak. The second thing we did was we did an iterative process. We'd run the 1000 iteration for a single SNR value and calculated the mean absolute error and root mean square error for the delay. And here we found that for higher SNR values, obviously there were no error in calculation of delay, but as we deteriorate the SNR values, the error tend to increase. And if we have a target of 1 millisecond as an error, because for us data rate was 1000 symbols per second, then we will have to decide upon the SNR value we can set based on the code we tend to use. Amod will further explain on the conclusion from this.
So based on the root mean square error that we received, we zoomed in on the 1 millisecond range because that is where we want to maintain the accuracy. And we found the different SNR requirements for the different coding schemes that we discussed. Over here, you can see that for Barker sequence, the SNR would need to be around -8 dB to achieve the accuracy of 1 millisecond. Similarly, for PN, it would be around -8.9 dB. For random sequence, it would have to be around -5.4 dB. And from here, we can see the most resilient of the 3 sequences is PN sequence, as it is it has more accuracy at lower SNR values. And that is how they are more resilient to the lower SNR ranges. So the final conclusion that we derived was that the delay computation is adversely impacted by the deteriorating values of SNRs. So we'll have to maintain a SNR value as per the channel, and it would have to be higher if the channel is more noisy. And choosing the right coding scheme would play an important role in delay computation, as this would help us in identifying the delay better based on their correlation properties. And based on these, we would be using the cross correlation between the transmitted and received signal to compute the delay for our short training sample, which would be pre-decided. And then we would run it on the actual data, and that delay which we have computed earlier will help us determine the actual data. This is a similar situation. A scheme is used in different technologies also, like Wi-Fi and Bluetooth. So our references that we used were more aligned to clock synchronization and time delay, and our further work would include estimating random delays and working on modulated sequences. That is all we have. Thank you.
Thank you. Thank you.
Thank you very much. Do we have any questions from the audience? If not, let's go for the next talk. Who is next?
Hi, Professor. I think it's us.
Yes, that's correct. Saurabh, go ahead.
Can you see my screen?
Yes, you're good. Go ahead.
Okay. Hi, everyone. We're the Adversarial Machine Learning Against Voice Assistant Systems group. We're supervised by Dr. Ying Chen.
Hi, I'm Selena.
Hi, I'm David.
Hi, I'm Saurabh. So a little background on this project. So this project aims to use adversarial machine learning techniques to attack voice assistant systems such as Google Home and Alexas. These devices are very commonly used nowadays. It can tell you the time, weather, control the lights, and a lot more. Basically, they hear your voice using microphones and understand what you said using machine learning techniques and answer your request. We will try to attack the devices by adding a small perturbation to your voice. So the objective. During this project, we wanted to study the security of voice assistant systems. More specifically, we wanted to generate and analyze adversarial audio samples to attack speaker recognition systems and then evaluate their speaker performance under attack.
The first thing that we had to do was identify our speaker recognition model to attack. We ended up choosing the X-Vector model, which is a state-of-the-art model that is built using a deep neural network. One of the advantages of the X-Vector model is that many proprietary closed-source speaker recognition models are built off of the same concept, so this gives us a look into some of the real-world applications. We implemented this all in TensorFlow, which is a machine learning framework that provides us many useful tools to help us build and examine our model. The first half of our project focused on untargeted attacks. The goal of an untargeted attack is to incite a misclassification. So for example, if I were to say something, the model would predict that the speaker is anybody else. While this doesn't seem very useful at first glance, we could consider a situation where speaker recognition is used for authentication. So say we have a voice assistant system that internally has a list of authenticated users that are able to request bank transactions. With an untargeted attack, I could trick the system into thinking that I am one of those authenticated users. We performed our attacks by adding a small perturbation to the original audio using the fast gradient sign method. With the fast gradient sign method, we determine what kind of noise we can add to most negatively impact the model's accuracy. We varied the strength of this perturbation, which we'll discuss more later in the results. The second half of our project focused on targeted attacks. The goal of a targeted attack is effectively to imitate a particular speaker. These attacks are much more powerful since they can be used for targeted identity theft, but due to their nature are also much more difficult to perform. These attacks are done iteratively by adding noise to the original audio sample until it's recognized as the target speaker. So essentially at each step, we add some noise to the audio, see what the model recognizes the speaker as, then add more noise such that it sounds more similar to the target.
So here you can see the results of our untargeted attacks. As David briefly mentioned before, we were able to vary the strength of these attacks by scaling them with a variable that we call epsilon. The plot on the left shows different epsilon values and their corresponding noise level in decibels. You can see that as the epsilon value increases, the average noise level increases as well and becomes less negative. The plot on the right shows different epsilon values and the corresponding model accuracy under attack. As the epsilon value increases and therefore the noise level increases as well, the model accuracy decreases. You can see that even at the smallest epsilon value, the distortion of the sample already decreased model accuracy by about 20%. If we play the two samples linked here, you can very clearly hear the difference in noise levels from samples generated with the lowest and highest epsilon value.
They had to learn to work from the
In order to determine the threshold at which the injected noise could first be heard, we conducted a survey, which allowed us to get a more subjective view of our data. We uploaded 9 different adversarial samples onto our website, each corresponding to a different epsilon value, and then asked people to listen and identify in which sample they could first hear the noise. You can see from this pie chart that the earliest detection was at an epsilon value of 0.000316, which corresponds to a model accuracy of under 30%. And these are the results of our targeted attack. Here's one of the samples that we generated, and it is one of the 9 that we have put on our website.
If you can run a computer, you can...
The graph to the right shows the average noise injected into a sample when trying to imitate the corresponding speaker. For this graph specifically, we chose a sample size of 50 speakers. The average noise level for these 50 speakers was about negative 21.6 decibels, which if compared to our untargeted attacks, roughly correlates to an epsilon value of 0.0316, which was easily heard by the human ear according to our survey results. So currently, our model simply generates adversarial samples and evaluates their efficacy. For future work, we'd like to conduct an over-the-air attack, in which case we would have to consider the room impulse response, which is essentially how our audio would be affected by the environment in which we launched our attack. By taking the impulse response into account, we would be able to make our attack as efficient as possible. We would also like to disguise our attacks to produce greater unpredictability. So right now, as you could hear in the sound files that we played, it's fairly easy to hear the noise that we've injected into our samples. By disguising our attacks, for example, embedding the noise within a song, it would make it very hard for the human ear to identify the attack, but the speaker recognition system would still pick it up.
Thank you. Any questions?
Okay, do we have any questions from the audience? If not, thank you very much, guys. This was
Thank
great.
you.
I guess that's a question in the chat.
Oh, there is. I'm sorry, I didn't see it. Let's see. Okay, so the any ideas for defensive mechanisms, guys? How do you defend against this?
Yeah, so currently one of the biggest things that our research doesn't look into is the effect of the roam impulse response. So naturally, the attacks become a lot more difficult just based on the nature of how they'd be done, because normally you would need some sort of speaker and some sort of microphone to project the audio. But since we had we were able to have direct access to the model, we were able to inject the audio straight in there. So naturally there already is some sort of like defense in some ways, but alternatively, besides that, we could add some sort of thresholds for the audio that could help the model detect that there's some sort of tampering.
Okay, thank you very much.
Thank you.
Okay, so who is next? I believe it's physical activity, right? There you go. Go ahead, guys.
Hi, we're the real-time machine learning-based user authentication via daily activities using wireless signals. Our advisor is Professor Ying Chen. Next slide, please. Hi, my name is Bhargav.
Hi, I'm Rashika.
And I'm Sachin.
So the goal of our project was to recognize human activity using Wi-Fi signals and collecting channel state information. So we wanted to implement a real-time system and create user authentication with a device-free approach. Our ultimate goal was to develop a deep learning-based user authentication to accurately identify each user.
As Rishika was talking about in the last slide, we were planning on we use CSI in order to measure the strength of these Wi-Fi signals. CSI, or channel state information, essentially measures how a Wi-Fi signal propagates through a room or through some medium from where it is transmitted to where it is received. As shown in the diagram here, you can see that many things change CSI, including the distance of any disturbances from the transmitter and the receiver, and the size of these disturbances. These CSI signals are separated into several subsignals by frequency. These are called subcarriers. And as a result of this, alongside the fact that CSI streams are separated between like transmitter receiver pairs, you get a large data stream. In our case, with 2 transmitters, 2 receivers, and 30 subcarriers that can be read, our setup gives us 120 individual streams of CSI data. In order to classify this large amount of data, we need something that can work in real time. In our case, we found out that an RNN, or a recurrent neural network, is best. A recurrent neural network essentially takes inputs over a period of time in order to classify them over that time frame. Specifically, we were going to use an LSTM, or a long short-term memory recurrent neural network, in order to compare a 1-second window of input at a time. The LSTM gives us more access to sort of clearing when our input is no longer needed at some specific length. In this case, clearing our input after that second window, or that segmented window, is over. Also, like we said earlier, 120 different streams of CSI data is quite a lot of information at once. And so in order to make this more manageable, we have algorithmically managed to segment the data. Specifically in our case, because the CSI data, like the wave data of the Wi-Fi signals in general, takes a waveform pattern, we've been using a rolling mean approach, or a rolling variance approach, where over a window of, let's say, 100 values, we check the mean of the CSS stream, and then from there we can detect the variance from that mean, and when it is within some threshold, we can say that some 0 point or some node, or we could begin or end a CSI segment. Therefore, taking the data points between those nodes and sending them off to our classifier.
So one aspect of our project was a visualization tool. And the purpose of our tool was to graph CSI data in real time. So with this tool, we were able to graph some sample CSI data, and we observed some spikes, which meant that the user was performing an activity at that time. And the CSI data that we graphed was for 270 subcarriers. So here we have 2 graphs. One is a graph for a user sitting, and the other is a graph for a user squatting. And we can see multiple spikes in these graphs, which are indicating that the user is performing an activity.
Hi, so over the course of the summer, we conducted 3 experiments where we had 4 participants each. We ran the CSI model, the channel state information model, for about a minute per person per activity. So in this slide, we have some key definitions. Simple sequence, which is the time sequence. It's the x-axis of how long the experiment is running, and we have the amplitude of the graph. And so the purpose of this slide was to point out how the amplitude of the graphs and the spikes within the graphs you'll be seeing in the next slide are very useful for recognizing and identifying users. Next slide. So in this slide, we have 4 graphs of people running. In each of these graphs, there is a different amplitude and there are spikes at different locations. So from these graphs, what we did was we ran an experiment for a minute for each person. And when we ran these experiments, we found out that each person had really small movements while they're doing this specific activity. Like when you're running, you might be running a little bit faster at some points in time, a little slower at some points in time. And based on these distinctions, we might be able to classify this data. Next slide, please. So as I was saying, how even the signals look different from, excuse me. As I was saying earlier, how even though the signals look similar from the previous slide, each person had a different amplitude and spikes at different locations in the graph. Based on these distinct differences, we would be able to understand the user identity because it's like a fingerprint to a person's. It's like a fingerprint based on how they react while they're performing a specific activity. Thank you. Are there any questions?
Any questions?
I have a question. So you said you conducted some experiments with 4 participants. Were you doing this at the same environment?
Yes, they were all in the same environment. So what we did was I had 2 specific, like a start and end zone. It's like an open space. And I had the users run in between those 2 environments for an entire minute. And once that minute was up, I would stop the experiment and I'd collect the data based on that.
Okay, so this will take us to another question. Do you think that the system will work? I mean, eventually we'd like to do some machine learning and to classify maybe the activities, or or maybe identify the user. So what if you take the system to another environment, like bringing it to the lab and ask some people to do the experiment, same experiment? Will it work? I mean, if it's already trained on another environment?
Well, yeah, that is a good point. If we did move to a different location, the data might be different because of the environment. But also, if for the purpose of the summer, I wasn't able to like pick that many locations other than my house.
Yeah, right.
But for the future, what we might be, if this project were to go longer, I would try to get data from different locations and feed that all into the machine learning model, so that these differences, we can eliminate these differences as much as possible.
Also, examining on the data side of things, because a large number of differences in location seem to be, or just like looking at data coming from multiple places, as I had data coming in from our mentors from the past year, as well as data coming in from this year. It seems that location predominantly changed rather than amplitude, the sort of like the median value of the CSI wave. And because we're working on a variance-based system, it seems like accounting for that, the location will have less of an effect than users' actions or the user's own individual disturbance to the CSI system.
Oh, okay, thank you very much.
Thank you very much, guys. Who is next? These are next, right?
Yes.
I think we are the 5th group. We are fine. I mean, we can go next, no problem.
Yeah, you guys are next. Go.
So guys, I'll do sharing. Okay. Hopefully you can see my screen.
It's all up.
Good to go.
All right, so we are the B project group. We are advised by Professor Martin and Dr. Howard. I am Murtada. I am a PhD student here at WinLab.
Hi, this is Tom. I'm just graduated from Rutgers.
Justin, and I'm studying computer science at Rutgers.
I'm Joseph. I study electrical engineering and physics. I'm a senior.
So recent research showed that the bees are using the Earth's magnetic field for navigation and also for maintaining their orientation when they are flying from one point to another. In this project, we're trying to explore if the bees can detect dynamic signals like radio frequency signals, and this will also help us to answer another question. That's if we'd like to find if the radiation at radio frequencies has any biological impact on the behavior of the bees. So in our approach, what we have done so far is we built a kind of smart bee feeder and we deployed it in the wild. So we built a prototype of a bee feeder and we deployed it at a bee farm that's just across the US one. And we equipped it with many components, as you will see later in these slides. And we also equipped it specifically with a RF source that can generate radio frequencies, the magnetic field and the radio frequency signal. So at the moment we are generating static fields, static magnetic fields, and our approach is kind of in the wild approach, in which we don't capture or release the bees. We just provide them with food and associate with the food with the RF source. So when the RF source is on, the bees can find sugar water to eat. If the RF source is off, then they will not find the food that they like.
So in order to put our system out in the wild, we have to put together quite a few parts and then have it survive field conditions. So what we can see here are some of the components of our system. On the entrance tube for the feeder, I don't really have, yeah, perfect, there's the mouse, yeah. So we have an entrance tube where bees enter, and we have coils wound over that tube, which can create magnetic fields, either at a static rate, where they don't change for several hours. And we can also generate them at higher frequencies. Our initial testing will probably be at 1 megahertz once we test RF, but we can go higher than that. We also have a camera system, which is run off of a Raspberry Pi, and it allows us to log video of the bees entering and exiting the system, which will help us get a better idea of how the bees are interacting with the feeder. And then, of course, to run everything, we had to design an electrical control system. So we have a solar panel, which is pulling in power, more than enough power. The problem is we have to distribute it across multiple things. The Raspberry Pi has its own power requirements. Everything has power requirements. You'll see that later. And then lastly, we also have the ability to measure the magnetic fields produced by the coil at any time, so that we can make sure that the coil is operating, and we can also know exactly what the bees are reacting to on the video footage when we look at it later. Next slide, please. So I was in charge of the field generation, and I designed a 700-turn bunch solenoid in order to create our magnetic field. The static magnetic field is about 5 times that of the Earth's natural magnetic field, the magnetic field that allows compasses to point north. And this design in particular was chosen as you can see in the picture of it, there's quite a few open spaces where you can see the bees as they go up and down the tube. If we wound a conventional solenoid continuously down there, even with spacing between the turns, it just wouldn't be as legible. The trade-off is the magnetic field is less uniform. You can see below there's a nicely lined up graph showing the intensity. However, those bumps are still pretty negligible, and it's definitely worth it for the video footage. And then just recently we finished designing the RF coil, which is a smaller helical antenna. It makes 10 turns down the length of the tube, and it sits underneath the larger hand-woven static coils. And that can be driven at a megahertz up to a gigahertz or lower. And it's going to be completely invisible to the camera, so it's not a concern because it's very fine wire. And I should mention, that the field generated by the RF coil is about 100,000 times weaker than that of the static field. So 20,000 times weaker than that of the Earth's magnetic field. But the interesting thing is that previous studies have shown that certain systems can detect that. So we're hoping to see results there. Sorry, next slide. Yeah.
All right, I'm Justin, and I've been working on the code for this project. So from the very beginning, we need to find a way to quantify the behavior of bees through video. So we've done that by simply counting the number of bees as they show up in the video. So if you look on the left-hand side, we have our sample feeder. So we have our current tube design with the coils wrapped around it, generating the field. So what we've done is we virtually segmented this tube into 4 different sections. So we can do individualized bee counts on these 4 different sections and generate a graph, as you can see on the right-hand side, where we can come up with percentages of total bees found in each segment. With these percentages, we can come up with estimations of how far each bee walks down this tube. The left side of the tube is where the entrance is, and the right side is where the sugar water is. So we want to track how far the bees actually walk down this tube to see how they react with the field. All right, next slide. Another way of quantifying this behavior is to actually track their movement. So what we've done is we're prototyping this, and we printed out these tiny 2mm by 2mm marker codes, as you can see. They're basically small QR codes. And what we're going to do is we're going to superglue it onto a back of a honeybee. And then as these bees walk down this tube, we're able to use computer vision software to pick up on these tags, and then also in turn pick up on how these bees are actually walking down this tube. So we don't know how the bees are going to walk down this tube. They might be walking zigzags and circles. We don't know yet. We're trying to see that, to see if they interact with the field differently. All right, and you can see, or you can go back. Sorry, you can see that in the red circle, the software is actually able to track these bees. We're pulling fake bees that we printed out with tags attached to the back of them. And we're going to plan on putting this into practice soon. All right, thank you. Next slide.
Hello everyone, this is Tom. So to observe the bees and to conduct the experiments, we do not want to be physically there standing with beehives, right? So we have our electrical control systems. So on the right of the slide, we can see basically everything that is needed. We have our pumps, we have a Raspberry Pi, coils. So basically everything is driven by the power from the solar units, which is shown in the slide 4. So if you're interested, we can go over that in detail in our post-demo sessions. Of how we control the Raspberry Pi, the on and off of Raspberry Pi based on the daylights, and control the 2 relays for the static field coils. So next slide, please. So PCB design. So what is PCB? PCB is short for the printed circuit board, which we can develop to make it do things that we want them to do. So in this case, to control the systems. So there's a specific software tool that we can use, which is called Eagles. Before we build the circuit, we figured out how to make the relay connections, which is shown in the figure 1, and we build our own Eagle libraries, which is the part we spend a fairly amount of time on it. The result is shown in figure 2 and 3. Figure 2 is the symbol in the schematic design, and figure 3 is the footprint in the board view. Next slide, please. So to build a circuit, we used figure 1 as our guideline. It shows a design layout which is developed by Professor Howard, and figure 2 shows the schematic design in Eagles, and figure 3 shows the board view. So it still now looks kind of messy, but it's still not done yet.
So one thing that's important to get across is that we want to scale this across multiple feeders. Right now we have our test feeder out in the field. The summer is still going on, so we plan to deploy more. But the current one, as seen up in the top right, is it's built out of Lego bricks, which was wonderful for prototyping. However, it's a little leaky, and if we want to build multiple that are identical, it becomes a hassle. So another thing that I was doing was designing a 3D printed version of this. We can see down in the bottom, there's a quick render of one potential option. Pretty much what I did was I changed the feeding area. We have it's not particularly visible, unfortunately, but it's a serpentine track for the fluids to flow through, that being the sugar water, the wash water, the bitter water. But this allows more surface area for the bees to come in and feed. We found that the bees don't like being too bunched together inside of the feeder. So there's a little more space. It's also, if we want to, we'll be able to put a camera directly over this area as well because it's a nice uniform flat surface. And yeah, the nicest thing is once we have a settled design, we can just press print, wait 6 hours, and we're done. And we can do this over and over again.
So for ground truth purposes, we also are using a wireless sensor node that's peptide, which is designed at WinLab. So, and I attached a magnetometer to it, as you can see here, and we put it in the tube in order to measure the magnetic field strength continuously. Also, we built a Python script that takes the data from the received by receiver, which is this one, and plot and display the data or the magnetic field strength in real time as shown here.
All right, so here are some recent findings that we got. So these are two graphs from the days of July 25th and July 26th, and we just did some generalized bee counts. So just counting the total number of bees found in the tube at each given moment. So if you can disregard the outliers, which can be cleaned up with software, you can look at these concentrations. The general concentrations look quite similar from day to day. And that might mean that the bees are finally starting to associate the field with sugar water. However, next slide, please. This project is not over. So we're going to continue trying these experiments and continue working until at least the first frost, which will happen sometime in October. So by then, hopefully we can gather more data and also find more correlation in the behavior of bees with the field. Thank you.
Thank you very much.
Thank you, guys. Any questions from the audience? If not, we can go. Yeah.
I would just quickly like to add, yeah, as Justin mentioned, this experiment isn't over, and even when the frost does come, we have further avenues to go on to looking at the hives themselves as they go through the winter, and we'll probably have a third feeder revision for next spring. This is the second year of the experiment, so hopefully we'll get something.
Yeah,
good. Thank you very much, guys. Our next talk is the FPGA and spectrum sensing and modulation recognition.
All right, can you guys see my screen?
Yeah, Ryan, go ahead.
All right, we are using FPGAs for spectrum sensing and modulation recognition. I'm Ryan.
Hi, I'm Johan Lee.
I'm Sid.
Hi, I'm Jacob.
So a little background. So here I will explain a few terms that will be used throughout the presentation. So modulation scheme. You can think of this as the language that a device speaks. This will tell us how the device communicates. IQ data. These are the noises that are coming out of the device's mouth. Putting these noises together in a controlled fashion makes a language. Similarly, putting IQ samples together in a controlled fashion makes a modulation scheme. SDRs, or software-defined radios. These are the ears that hear the noises. An SDR will listen to the radio environment and jot down what it hears as IQ data. FPGA, or field programmable gate array. Most wireless devices have very specific hardware that allows them to communicate. Regular computers can approximate the performance of this hardware, but FPGAs can do this better.
So the goal of our project is to use the idea of machine learning to recognize different wireless devices on the environment by processing the signals transmitted by them. And we're gonna construct a matched filter implemented in Go language and use it in FPGAs to compare the performance against the machine learning based modulation recognition. So by using the software-defined radios, which we introduced before, we can record the IQ samples from different wireless devices, such as phones we're using, Bluetooth, earbuds, laptops, and also Wi-Fi environments. And all the data we collected from SDRs will be used as training data to the set of neural networks, and also classify them based on their different modulation schemes. Next, please.
So for the data collection. So the goal of this is to mimic wireless transmissions in a mostly controlled environment to be used later as training data for a modulation recognition neural network. For physical transmitting and receiving, we use the USRP X310 and V210 SDRs that are attached to the WinLab orbit grid. To generate the Wi-Fi IQ samples, we use the wireless toolbox library in MATLAB. To transmit and receive the IQ samples at the software level, we use the UHD sample scripts, and we use OEDL to manage all of the devices in this experiment. So the experiment. So to the left, you will see some properties of our experiment. To the right, you'll see a picture of WinLab's orbit grid, which is a collection of devices at WinLab used for experimentation. Each square with an X on it indicates a device that we are using. And the green lines showing up here indicate the distances between the devices that we use in each iteration of the experiment. Data collection flow. So first, we're going to copy the Wi-Fi IQ samples from the central node to the first set of nodes, which is the transmitters. Then we're going to transmit the Wi-Fi IQ sample files via USRP to the receiver nodes. And if you look in the middle of step 2, you will see a cloud that represents a real-world noise. Running this experiment on the grid gives us the benefit of real-world interference from other Wi-Fi devices. Using real noise in our data makes our neural network more resilient. In other words, it will be better at distinguishing between modulation schemes when there's noise involved. And for the final step, we copy the received Wi-Fi IQ samples to archival storage.
So I'm gonna introduce how the matched filter works. So a matched filter is easy to understand. For example, we use water filter to clean the water we drink by eliminating the impurity. Here, the matched filter has the same function, but it's for the radio signals. In signal processing, we use it to get rid of the noise which is meaningless or unwanted from the signal we received, just like purifying the water. So for technical parts, what it really is, it's like a process to detect whether a particular piece of known signal exists in an unknown and noisy signal we received, and to check if the output of the filter is the same as our template signal. It can also show us if the unknown signals we received matches with the modulation scheme provided locally. So for us, we have different type-based modulation recognition. First one is neural network-based modulation recognition. And the features of it is it requires little prior information and can be used for the signal we don't even know. And the second one is the matched filter-based. It requires more information and need to be used on the signals we have seen before. And we need to compare the performance of two different type-based methods and make sure that the performance of the neural networks is at least comparable to that of the matched filter for the signals we know some information about.
So we represent the signals in this project with pseudo-random numbers. And to generate these sequences, we made a linear feedback shift register in the programming language Golang. This is an algorithm that creates random data for the signals by taking input values and generating bit sequences that are combinations of zeros and ones, as you can see in the example pictures to the right. So since these bit sequences vary based on the input, each signal has its own unique sequence attributed to it. And this is important because we can use the previously mentioned matched filter to search for bit patterns in these sequences and help determine the signals from the wireless devices.
So as for our future goals for this project, one of them is using a match filter to identify the different modulation schemes for random sequences. So the way this would work is we would generate random data using the linear feedback shift register that Jacob talked about. And this would be a very long string of bits of randomized zeros and ones. And then we would create a specific 8-bit sequence in modulation to use as a matched filter. And essentially what we would do afterwards is traverse the random data string and use the match filter to find hits within the random data. And our hope is to eventually be able to use multiple sequences as match filters at the same time to increase the speed of hit detection. And this ties into our other future goal of using match filters in conjunction with neural net data and FPGAs to classify devices. So right now we are currently using MATLAB to develop the match filters because MATLAB already has access to many built-in signal processing functions and libraries. And it's easier for us to compare the results of using match filters versus machine learning, since a lot of the neural net data collection was done in MATLAB as well. And then what we want to do is transition to using Go to make these filters, because Go is a higher level language, and its use of Go routines and channels would allow our programs to run in parallel and much faster. And this would be very beneficial to us, especially if we want to use multiple filters concurrently, right? And then finally, what we want to do is compile our Go filters into Verilog, which is another language. And we would do so via our Go to Verilog compiler that Professor Martin provided us. And we're going to do this because Verilog is used to run on FPGAs, which is the namesake of our project. And from there, we can use FPGA to detect radio frequency signals of various devices. Any questions?
Thank you very much. Any questions from the audience?
Hi, I have.
This is Dan again.
Go ahead.
The classification of devices that you do is at the level of the modulation that they use, or can you do more granular classification?
Yeah, so it is at the modulation level. So like BPSK, 16 QAM, stuff like that.
Great, thank you.
Mm-hmm.
Was there another question? I think there was somebody else.
Yeah. Hi, this is Marish here.
Yeah, hi, Marish. Go ahead.
So I wanted to ask, what was your reason behind selecting Go? Why not C++?
Okay, so I'm not sure. Guys, go ahead. Try to answer that.
Oh, yeah. Well, my understanding is Go, it has access to what is called Go routines. And I think the equivalent in C++ is basically threads and multi-threading.
Yeah.
I think we could use C++ too, but what we found is that using Go routines will allow us, our goal eventually is to be able to use multiple filters and run them concurrently. So we thought that using Go and utilizing these Go routines and channels would allow us to do that.
Okay. I'm not much familiar with Go, so can you just briefly explain what are Go routines?
I'd say I compare it to the equivalent of like multi-threads, like thread execution in C or C++. It's similar to that.
So the big advantage from my understanding is that Go routines will actually map much better to an FPGA when we compile it into Verilog. Whereas opposed to threads, there's not necessarily a real translation for that to run on an FPGA.
Okay.
Yeah, the other main reason we're using Go is because we can compile it into Verilog, which can be used for FPGAs better.
Okay. Yeah, thank you.
Thank you very much, guys. Okay, so our next talk is the intersection simulation. Are you guys ready?
Yes, can you hear me?
Yep.
Yep,
ready?
Yeah. Yeah, let me just pull up. All right. So hello, we're the intersection simulation group. I'm Mark.
I'm Alan.
And I'm Patrick. So for our project today, we're going to explain what our intersection simulation is and why we built it. So one thing, we wanted to develop a smart city intersection simulation that mimics the intersections in New York City that are 120th and Broadway and 120th in Amsterdam. These intersections have a physical scale 15:1 model in the orbit room at WinLab, and our virtual simulation of that is based off of the WinLab model. Our simulation aims to be a testbed for self-driving research. A couple of the reasons for that: one, using a simulation instead of a real car is not only cheaper, but it's potentially safer, depending on if the model makes mistakes or things of that nature. Also, one of the things that we like about a simulation as opposed to real cars is that we're able to be more flexible with what variables we choose and what we don't in our simulation. And one of those factors is the ability to emulate human driving at our own pace in this simulation. In order to do that, we opted to use a traffic simulator, which allowed us to get accurate traffic models of these intersections, and thus giving the self-driving car a sense of human drivers around it while it's learning in the simulation.
All right, so to create a realistic testbed, we utilize three main technologies. First is SUMO, the simulation of urban mobility. Sumo is a traffic simulator, as Patrick mentioned earlier. This is what we use to create our traffic models with various routes. The idea was to simulate daily traffic that the two intersections may see in real life. We also use Gazebo, a robotic simulator. We use Gazebo to build our entire world out. So this is where you could visually see the roads, lanes, and cars in 3D. A big part of our project was not only to build a world in Gazebo, but also connect it to Sumo. So we could have the traffic models we built in Sumo be seen in our 3D world in Gazebo. To do this, we used ROS, or Robot Operating System, to communicate between Sumo and Gazebo. The specific version of ROS we used was Melodic.
So here we have two pictures of the physical model intersection at the orbit room in WinLab. These intersections are an accurate model of the intersections in New York, and we ended up basing our virtual model on this. So on the left, you have an overview of both intersections, and the closer one is Amsterdam and 120th, and the farther one is Broadway and 120th. The right image here gives you a closer look at the intersection of Broadway and 120th. You can see from both images that the roads are not just straight lines, but there are other elements that you would see in like an actual road, such as like crosswalks, parking spaces, and traffic lights. So here we have our actual virtual model that we built in Gazebo. So the top left picture is the virtual model of Broadway and 120th, and the top right is the virtual model between Amsterdam and 120th. You can see that they're very similar to the physical models in the orbit room. The bottom left image here is a closer look at the intersection at Amsterdam and 120th. It just lets you see the lines better and see the traffic lights as well. And then finally, in the bottom right, you'll notice that this is an entire overview of the intersection. You'll notice that there are roads on the outsides. While these are not actually present like in the New York intersections, these serve as a path for the model cars to exit and re-enter the intersection to keep this simulation in constant motion.
All right, so this is a video of our Sumo traffic model. Okay, so here we can see the traffic lights from both intersections are operational. Notice how the cars attempting a left turn creep up into the intersection, mimicking drivers in real life. You can also see that there's more traffic along the vertical roads. This is because Broadway and Amsterdam are major avenues, while 120th Street is only a minor cross street. Currently, we are only using passenger cars, but we could explore different models with other vehicles in the future.
Okay, and here we have a video of the results for our connection between Sumo and Gazebo. Yeah, so as we see here, I'm loading up what we call this the hybrid simulation, as I'll explain a little bit later. And what this loads up is not only Gazebo and Sumo. As you can see, the Gazebo world is currently empty, something that will also be touched on. But what's important is we'll see this is the Sumo road network that Alan was describing earlier. When we click the play on it, we have the cars start moving in Sumo. And if we go back to the Gazebo model, we'll see that the cars are spawning in the places at which the Sumo cars are driving. So this is the main goal of our project, which is to be able to have that human driving emulation in there. And that's something that we're able to accomplish with Sumo and Gazebo being connected via ROS. Now, one of the things I mentioned earlier is the fact that the Gazebo world is actually empty. The reason for that is one of two things. One, when we were working on establishing the ROS connection, we worked heavily off of an implementation developed by Mario Garzon and a couple of his French colleagues that focused on connecting Sumo and Gazebo. One of the issues we ran into is our world was incompatible with their implementation. So while we were working on the world alongside the implementation, we found out when we connected them that there were some issues, and therefore the world model was somewhat glitched and didn't get transported through. And so one of the things that we do immediately in future work is to rebuild our world in the format that the intersection simulation connection was established, which would let us have not only the cars spawned from Sumo, but also the world that we built from Gazebo.
So for the next step of our projects, we would like to incorporate the self-driving car group's work with our work. Their self-driving car would then have the opportunity to drive around our simulated environment, and we would be able to see how it handles common traffic rules such as traffic lights, lane mergings, and right-of-way. Another thing we can add in the future is street parking and pedestrians. If you notice in our simulated world on the bottom right picture, there are street parking spots along 120th Street as well as crosswalks. To provide a more realistic simulation, we could add these features into our traffic model via Sumo. Lastly, we would sync up our Sumo traffic lights with our model in Gazebo. Currently, they're not synced up because our Gazebo world is bugged, as Patrick mentioned earlier. We would like to thank Jenny Shane and Yvonne Seskar for their guidance and mentorship through this summer. And we would also like to thank Mario Garzon for his work with the hybrid simulation. Thank you, and any questions?
Thank you very much, guys. Do we have any questions? If not, let's go to the next talk, which is using FPGAs for machine learning acceleration.
Hello, everyone. Can you see our screen and hear me?
Yep, go ahead.
Hi, everyone. We're the Field Programmable Gate Arrays for Machine Learning Acceleration project. My name is Milos.
And my name is Michael Yakubov.
So a little bit of background information before we get started with our talk. So a Field Programmable Gate Array, or FPGA, is a hardware component that allows for customizable circuit implementation. Because of this, it is reprogrammable in nature, which we will later show why it is of interest to our particular project. Machine learning, or ML, so obviously the study of computer algorithms that automatically improve performance through training and experience. A neural network, or NN, is a web of node structure that's used for machine learning, designed to improve classification accuracy by training with data sets. So it's similar to the way that humans learn in our human nervous system, through trial and error and experience. A central processing unit, or CPU, is a main hardware component responsible for all the processing and executing of instructions, essentially like the brains of a computer. And a graphics processing unit, or GPU, is another hardware component that's designed to rapidly process those same instructions in parallel. So it's used often for graphics-heavy programs and operations. So the motivations for our project is that machine learning is typically performed using those two hardware components that we mentioned, the CPU and the GPU. Think in your laptop, for example, laptop will usually come with, you'll see i7 cores and different CPUs and graphics cards that are NVIDIA or AMD, for example. So we wanted to look at the performance of machine learning when executed on an FPGA. The logic behind this is that to make a specific hardware component that is uniquely designed to run for an application is costly and expensive, although it's definitely the best in the terms of hardware. The idea with an FPGA is if they can be reprogrammed to work optimally for a specific function, it's cheaper to use that way, and it would be much faster than using a GPU or a CPU, which is, again, multi-use, but limited in the extent of the performance of each use. And so our methodology for this project was to start, of course, by first examining machine learning and diving into neural networks. And we began with a simple perceptron model, which is a machine learning algorithm where the results of the data are classified into two options. So it's binary in that sense, and the options are yes or no, on or off, 0 or 1. And we use this to classify sonar data, whether a mine was present in an area. So like a sea mine. This was written in Python and deployed on 3-layer neural network. So we had an input layer, a second hidden layer, and an output layer that put out into 10 classifiers. So we used a handwritten data set that is called the MNIST data set, where you have these handwritten digits. And we wrote this in Golang.
So on to some of the issues that we faced. One of the largest issues is that integer arithmetic is preferable on an FPGA as opposed to floating point arithmetic. This is because a floating point arithmetic would require that on the FPGA we call a library every time, which would take too much time, and that defeats the purpose as we're trying to increase the speed of machine learning. So in order to implement a conversion to integer arithmetic, we started by switching from a sigmoid activation function to a rectified linear unit, or ReLU activation function. As you can see, the graph on the left is a sigmoid function. For any inputs z, the sigmoid function outputs a floating point number between 0 and 1, whereas ReLU, for any input z that is negative, it will output 0, while for any input that is positive, it'll output the input z itself, which is good for our purposes because it has the potential of outputting an integer. as opposed to always a floating point with sigmoid. However, this led to an even larger problem that we had to deal with for a while, known as dying ReLUs, which is when all of our inputs into ReLU would be negative, and therefore when it outputted from ReLU, it would be 0. And this happened during our gradient descent portion of our algorithm, which is the optimization. It's during each iteration of our program, it would update the neural network in order to become more accurate. Next slide, please. However, once we fixed this, we had some pretty good results. This is a diagram of what our neural network looked like. We had 784 inputs. Each of these inputs was one of the pixels in the 28 by 28 image. Each pixel was then sent to each of the 100 hidden neurons. This is what is known as a fully connected neural network, as each input went to each of the neurons in the hidden layer. An operation was performed in between this step. That would be the ReLU function. And then again, from the hidden layer to the output layer, where we have 10 outputs, another operation was performed. And each of these 10 outputs corresponded to one of the 10 digits, 0 through 9. And this is how our neural network would predict what the digit in the input image, what the handwritten digit was. The learning rate that we used for this neural network, we found the best learning rate was 0.0005, and we would scale the inputs to be from 0 to 10. It used to be from 0 to 255 as a pixel value would be. The training ended up really successful. It would train in around 6 minutes and 45 seconds, which was a lot faster than our sigmoid function, which was at around 10 or 11 minutes. And it predicted in around 45 seconds with a score of 9,732. This is out of 10,000 possible images, so it had an accuracy rating of around 97%. So what's the future hold for our project? We're going to continue implementing the fixed point arithmetic and scaling the values so that it would no longer rely on floating point arithmetic, and we would fully go to integer arithmetic. We would also want to pre-process our input data. This is the pixel data from the images. We would do this on our CPU and then deploy it onto the FPGA. Then we would compare the time that the neural network took to train on the FPGA as opposed to a CPU or a GPU. We would do this on the Rutgers iLab systems. And then once we do all of this, we would like to move to more complicated machine learning models. We could implement this with a machine learning model that could recognize colored images. A special thank you to our mentors, Richard Martin, Jennifer Shane, and Prasanthi Madala, for guiding us throughout this project and helping us. If you have any questions, we will be happy to take them at this time.
Thank you very much. Do we have any questions? If not, let's go to the next presentation, which is the virtual ROS-based self-driving car model.
Can you see the screen?
Yeah, we can see it. Can you guys hear me?
Yep. Yep.
Oh, perfect. Right. Hi, everyone. We are the virtual ROS-based self-driving car model team. My name is Victor Abril. Our teammates are Nathan Yu and Shunak Arnwala. The project that we worked on for the past summer is part of a bigger project that focuses on developing a virtual city environment simulator. Our part of the project focused on developing the self-driving cars of the city environment. We incorporated ROS, which is a robot operating system to control the car models in the virtual city environment. And we also use machine learning algorithms to create the self-driving car models. We chose a car model, as you can see in the picture, which is a Prius model. And this model had many different sensors, but for simplicity purposes, we decided to use only the front camera. as input for the self-driving algorithm. I previously mentioned that we're using ROS, but what exactly is ROS? Well, ROS is a framework that works on top of the operating system that allows us to code hardware components of a robot. This simply implies that we can create programs for robots without having to deal with the hardware. So typically when you program in ROS, it encourages you to separate your code out into different components that each do one thing. Each program that you write that does this one specific task is called a node. In this specific example, we have node 1, which is is an example of a script that could read the odometer in the robot's wheel and tells you where the robot is relative to where it started from. And then node 2 is an example of a script that is a path planner, which basically tells you how to go from point A to point B. And node 3 is an example of a code that, given a certain velocity command, tells the motors to move in a certain way to achieve that velocity. Now, the way in which these nodes communicate with each other is through topics. Topics is kind of like a named channel that nodes can send data onto one another, onto other nodes. So in this example, node 1 is communicating with node 2 through topic 1, which is named autumn. And node 2 is communicating with node 3 to topic 2, which is named CMD vel. Now, the data that actually gets sent to these topics are called messages. Here in this example, we see that node 1 sends messages that are XYZ position coordinates to path planner. And then the path planner tells the node 3, which is the motor controller, how to move. So in this case, it's move 0.2 units and then not turn at all.
So now I'm going to get into why we needed to collect data and how we went about collecting this data. So in order to train our model, it needs to learn how to drive using the camera images and steering wheel positions. And the more data that the model studies, the better the model could drive itself. And to do this, we recorded ourselves driving our Prius model in the simulation, and we stored the camera images and steering positions in files called bag files. And these bag files are ROS built-ins that are used for data collection. So if you see in the bottom left, the general setup we used is where we could see the front camera on the left and the simulated environment on the right. And in the bottom right, we have a before and after of processing the images from the camera so that the model can use this data for learning.
Okay, I'll take you guys through our actual machine learning model. So as Nathan mentioned earlier, what the input we are using for our model is an image input from the front camera, which you can see. So we pass this input through our neural network. It processes it, and the output of the neural network is actually a float value, which lies in the range from -1 to 1. This is the steering value, which will determine how much the car has to steer to the left or to the right, and therefore guide it along the road. Another important thing to mention here is that we use a loader data set, which would randomly sample through all the images that we have recorded previously and then train the model on that. This was actually an important process because this helped us to save up on space and reduce space complexity and train the model faster. This is the actual data pipeline that I'll talk about because this is how we are actually implementing the model in our system. So as you can see that from the car through the topic image raw, we are getting the image, which goes into our predictor node, which we scripted. This has the model initialized in it and has all the weights file in it that we have saved after the training. The image passes through the model and generates the steering value, which we pass over the topic steer to the drive node, which in turn makes a separate control message, which then guides the car around in the cityscape. Now Nathan will take you through our results that we obtain after training the model.
Yeah, so on the left, we have our first training video that we recorded. This is after 10 training cycles using 15 bag files worth of data. As you can see, like the car is sort of able to follow the path without lots of training. but it's a bit slow and you can see it's wobbling back and forth. So now we train the car using 20 training cycles and 37 back files worth of data, which was much more than the iteration on the left. And already you can see that there's a really big difference in driving behavior. The car is driving a bit faster and following the path much more smoothly. And this is sort of what we expected to see, that with more training and more data, the model will be able to learn and predict better driving behavior than what we even recorded during data collection. And yeah, that's it. Thank you.
Thank you very much. Do we have any questions? If not, let's go to the next presentation. Go ahead, guys. You're good to go.
Hopefully you guys can see that.
Yep.
Cool. Hi, everyone. We're the WinLab Smart Intersection intern team.
I'm Nicholas.
I'm Kevin.
And I'm Brian.
Our group was advised by Yvonne, Zoran, and Jenny. And we'll start off by introducing our project. All right, so Smart Intersection uses object detection algorithms on video taken from traffic intersections to locate and track vehicles. This process is called inference, in which vehicle movements are analyzed and the results are used to determine where vehicles are coming and going to quantify traffic flow for that period of time. Ultimately, we want our project to be able to help transportation departments manage the traffic in their cities by providing insights into how traffic patterns change over different hours and days.
And to that end, we had a few goals for our internship. We wanted to be able to perform inference, which would allow us to track vehicles using machine learning on video footage. We wanted to create a distributed system where we perform inference on one machine and then send the results over to another machine for recombination with the original stream. And we wanted to use the results from our system to quantify traffic flow information.
To accomplish those goals, we took advantage of various existing technologies. Our project is built upon NVIDIA DeepStream, a software framework used for building real-time, intelligent video analytics pipelines. It's specifically designed to run on NVIDIA GPU hardware to take advantage of their advanced video processing capabilities. DeepStream makes it easy for us to implement a working object detection system, and the detector that we use for our project is called YOLO.
To get more into that, YOLO is an object detection system designed to be fast enough to run in real time on live video, and we use version 3 for our project. Due to the way its underlying neural network is structured, and just for a bit of background, a neural network is used to classify certain objects based on trained data in the past. It only needs to pass inputs through its system once, hence the name. This results in very fast inference times and also allows the algorithm to globally reason about objects and their context within the scene. This makes the algorithm more successful than others at recognizing new representations of objects it was originally trained on. And then as you can see in the top image, initially many possible choices for the location of desired objects are present, but this continues to be filtered down through some techniques in YOLO until a good fitting box is centered around the object.
We use other technologies such as AMQP, OpenCV, and NTP as well, and we'll give a brief summary on each. First, AMQP is a messaging protocol that lets us send data from one machine to another. We use the PubSub messaging pattern where we publish the data to a message broker that the other machines can subscribe to. Next, OpenCV is a library that allows us to draw bounding boxes around the detected objects via inference. We also use it to label object types and how confident our model is of its predictions. Finally, NTP is a network protocol that lets us synchronize the system times on various machines to the time on a reference machine. We do this to make sure that the boxes we draw using OpenCV are timed correctly with the original video.
Now let's cover our implementation. This diagram is a high-level depiction of how data flows through our final system. To start off, we have footage coming in from a video source. This video gets streamed to both our inference server and our viewing client. On the inference server, video is fed into our custom DeepStream application. The output inference data is published to a message broker on the same machine. The viewing client subscribes to the data published to the broker to retrieve this output data. The client runs a multi-threaded process, more on that later, that writes the inference data to memory and combines it with the original video stream. To allow for this, the clocks of all these machines are synchronized using NTP. The major components that we developed during our internship were the DeepStream application and the multi-threaded reader-writer implementation of our viewing client. Let's go through our DeepStream app. The data pipeline we constructed is made up of various elements. A source bin decodes all video sources and feeds them into a stream multiplexer, which adjusts the resolution of the video to match the resolution used for inference. As videos arrive at the multiplexer, system timestamps are taken for synchronization client-side. Multiplex data is fed into our primary GPU inference engine. This performs inference on the video scene using our chosen object detector, YOLO v3. The engine spits out predicted object locations, their predicted types, aka their classes, and how confident the model is of its predictions. Objects detected are sent to a tracker. The tracker attempts to follow detected objects as they move across the screen and assigns them unique ID numbers. This tracking data is fed into an analytics plugin, which takes tracked objects and determines what direction they're moving in and whether they have crossed certain boundaries. This is useful for us when figuring out when and where vehicles are entering and exiting the intersection. Lastly, all the data we recorded from the previous steps is packaged together into a message payload. The application takes this payload and publishes it to our message broker for transfer to any number of viewing clients.
All right, so as we mentioned before, our viewing client uses a multi-threaded implementation with 2 threads to allow us to process inference data and video in parallel. We can think of multi-threading in the form of an office environment. Our writer thread is sub to our message broker, almost like receiving an email from the manager. It takes in the message it receives, parses them for inference and analytics information, and writes this information to a queue. We can think of this as if only certain instructions need to be passed to our coworker, who will use the sifted information to perform their job. This queue is also a data structure shared between both the writer and reader threads and is used to pass information from the former to the latter. Also, the system runs in a loop, so the worker will continue to check their email to see if the manager sends any more information, and will continue to send instructions to the coworker as they come in.
The job of the reader thread is to add the bounding box information to a frame in the video once the information is received from the writer thread. The reader thread reads from the shared queue to get our inference output, and then back to our office example, this would be when the coworker receives the information sent over. It compares timestamps in order to make sure the output was inferred at the same time as incoming video. Once the reader thread has object information timed properly with the original video stream, it uses OpenCV to draw boxes around detected objects and label them with any relevant information, such as names and confidence in predicting that object. And then back to our office example, this is when the coworker does their instructed task and then checks their email again to see if any more information was sent over. This process continues until there is no more video remaining. And then here we have our sample inference run on our traffic footage combined with bounding box information. We're able to detect the vehicles moving across the intersection, which was performed, as we said, using YOLO v3 and DeepStream. The values in parentheses are the predicted directions of travel for that particular object, so north, south, east, west. Next to the confidence percentages, the client will also display any boundaries that have been crossed by the object. For instance, the zoomed in shot on the right shows a car that was detected as exiting the intersection from the south. These line crossings are counted to figure out how many vehicles passed through the intersection and where they were going.
All right, so future improvements we're looking to make to our system include training a custom YOLO model specifically designed to detect vehicles. The current model we use is a more general one, which is trained to detect a variety of objects. We're also looking to update our project from YOLO version 3 to version 4, as it comes with various improvements, but currently it's not supported in DeepStream by default. Lastly, we're looking into ways to use point clouds, which is a form of depth data, to increase the accuracy of our detections.
We hope you enjoyed this high-level overview of Smart Intersection, and there's a lot of details we let out for the sake of time, so if you're interested in the more technical aspects of our project, feel free to visit our website or take a look at our notes on what we learned over the course of this internship. Also, we'd like to give a special thanks to our advisors for their guidance, and a big thank you for everyone for making the summer so enriching. And if anyone has any questions about our project, we can answer them now.
Thank you very much, guys. Do we have any questions? If not, let's go to the next talk.
Hello guys, can you guys hear me?
Yes, you're good to go.
Okay, hi everyone, my name is Justin. I'm the machine learning for IoT group, also called as Maestro. My advisors are Shantanu, Professor Ortiz, and Murtada. So what you guys looking at is a normal weekday 9 a.m. to 10 a.m. occupancy distribution graph of a high school. The red dots represent the students who are currently in class. And as we all can see, the auditorium and museum and drawing room are currently empty. The 4 green circles represents the fire exits. Just in case of emergency, the students on the left wing could exit through the building via the left fire entrance. The students who are in the mid wings, they can access the building via the auditorium fire exits, and the students on the right wing, they could access through this fire entrance. But let's think about another case of scenario when there is a school assembly in session. All of the students are in the auditorium. So in this case, the only viable ways for students to leave the building is through the auditorium fire exits. This will lead to a significantly changing distribution of each fire exits, but the static evacuation routes remain unchanged. So is there a way that we can take advantage of this corridor? Is there a more effective evacuation route that will take that we can use for students to leave the building? Now that brings out the question: is there a way that we can build a system to solve that problem? Is there a way that we can build a system that can tell us the current occupancy distribution? Is there a way that we can measure like the hallway capacity? Is there a way that we can build a system that can quickly and safely disseminate the use formation to all the students? Is there a way that we can build a system to locate the source of emergency? To answer the question, to answer the current occupancy distribution, here's something that we can do. We can deploy a non-intrusive sensor throughout the floor, and we have to enforce those sensors have accurate readings, and we can collect and analyze those data in a central hub for hallway capacity calculation. We can measure the speed of human movement in corridor during class, lunch hours, exit times, and so on and so forth. And for information distribution, we can place lights on hallway floors, and also we can build a sensor system that can trigger the fire marshals when there's emergency occurs. And now, please allow me to introduce you SmartBox and SmartDash. On the left side, that's a prototype of our SmartBox hardware, and on the right side, it's called SmartDash, and this is a full stack framework. We'll go into details later. Before we jump right into the real-world application, I want to talk to you guys about the system design. So on the left side, SmartBox is powered by Raspberry Pi 3, and the data collection is enabled through an Arduino Uno connected to various sensors, which I will go into details later. The SmartBox has one function, which is to collect data at 1 second time intervals and send them to the centralized database. A camera is also attached for users' convenience while labeling, so that a video feed can be shown during active learning phase. A picture is taken from the camera every 2 seconds. The user can remotely turn the camera on and off by modifying the configuration file on the SmartBox. We intend for the camera to be turned off after the initial training phase, so as to minimize privacy concerns. For every 10 seconds, the SmartBox will issue a post request in JSON with 180 total sensor readings. Timestamps are given as UTC timestamps rounded to the nearest second. After we upload all the data to our hub, which is in this case is the MongoDB database, the SmartDash will comes into play. So basically, SmartDash is a full stack framework where it will generate 18 parameter graphs based on users' input. Those input, let me just go back to the previous slide. As you can see, users can input the box name, the start time, end time, and also the channel name, and then we can generate the 18 parameter graphs right here. And on the right side here, as the red arrows indicates, users could also select segments of data, and they can also enter a custom label for that specific time interval. And also, this is a list of sensor data that we collect. As you can see, we specifically let out camera feed and audio for the purpose of non-intrusive, because we believe we want to deploy those smart box in any private situation, and having a camera feed and the audio could be very intrusive. And this combination of sensors is also very affordable, which means we can produce at a large scale. And this is just another overlook of how users can interact with the front end with the database. As you can see on the right side, by inputting the right format, the time and the box name and the channel names, users can manually update the label to our database. Some applications of our project, one of which is to monitor daily activities. Smartbox, we can place Smartbox in homes of elderly people, which allowed us to monitor their health. And by using classifier, we can also monitor like what their daily activities are. Another good use of a future use of our project is the centralized AC system. The active learning can help understand occupancy schedules and comfort preference of occupants, which also allow us to save a lot of energy. Our future goals, hopefully we can deploy Smart Dash publicly, and we also hope we can simplify the interface for multiple Smartbox connections, and hopefully we can also deploy Smartbox on campus. And that's all. Thank you guys very much.
Any questions? If not, I believe we have one more talk on mobility first.
Yes, Professor.
Go ahead. Grab the screen, please.
So, hi people. My name is Naga, and I work for Mobility First project under the guidance of Dr. Ray Chaudhary for the internship program. So, coming to the project, the Mobility First project was aimed to provide a better architecture than IP address to accommodate all the mobile devices. So, by providing some efficient network services. So some of the challenges faced by this current IPA architecture are like multi-homing and host and network mobility. So multi-homing is a scenario where a single device can be connected to two or more networks, and it can have two or more IP addresses based on the network it is connected. So whenever another device wants to contact this device, it requires the network IP address to communicate with this particular device. So whenever this device is getting fluctuated between, it is getting frequently connected and disconnected between these available networks. Its network IP address is getting frequently changed. So it is unable to track the particular IP address of the device. So in order to avoid this drawbacks, the mobility first architecture was developed, and in the the project has mainly two phases. In the first phase, the design and development of the architecture was done, and now the current phase is to deploy the architecture developed into the real-time networks. So some of the key features involve. So as I mentioned, the network ID. So whenever the device connects and disconnects from a set of network addresses, its IP address gets on changes. So in order to track the device, the mobility first architecture uses a particular ID known as globally unique identifier, which is assigned to each and every device globally uniquely by service of naming convention service. And using this GUID, the architecture can separate the name and address of each and every device. So coming to the work I have done in the project, I have worked on two major components in the mobility first architecture. One of them is mobility first router, and the other is the GNRS server. So the mobility first router is a general router which is configured in the CLIck programs. So CLIck program is a development framework in which a device or a node can be configured with the help of elements. So the elements help the help us to provide the attributes and the functionalities of each and every device independently. So once the elements are created, we can use the elements to configure a particular device. And coming to GNRS server, it is also the full name of the GNRS server is the Global Name Resolution Service. So this service is mainly used to convert the GUID into the network address from which the device connected to the required device can be communicated with. So the key features of Mobility-First Router are it uses a generalized storage aware routing, and it has the hybrid network routing in which it can use GUID based routing and the network address based routing. And coming to the GNRS server, the GNRS server uses hashing techniques to convert the GUID into the set of network addresses. So as per the project and my roles, I have to create a communication link between the Mobility First Router and the GNRS server. So in order to do that, I have developed a UDP socket programming in C++ and Java to create elements and modify the codes of the particular GNRS server and the click sort Mobility First Routers developed in the click software. So the click software is generally involved with the C++ language. So every element in the click software is coded in C++ language. So I have to use C++ and Java in the entire UDP socket programming for this project. So I was not able to provide the complete Mobility First Router program. So what I've done is I've taken a time source which will be generating a given GUID which I got from a net by Googling. So I randomly generated this GUID and I tried to send this GUID to the socket UDP. And once this element received the GUID, it tries to contact the server running on this local. For now, I'm trying to run the server on the local host on the port 5000. So it tries to contact the server and waits for the server to respond. So once this UID is received by the client, it will send a query to the GNRS server to get a set of network addresses. So in the in the Java server UDP socket programming I have developed, I tried to modify the code to make some hashing techniques. Hashing functionalities to get some network values. So since this is not a valid GUID, I got different values. So whenever I try to run the client socket, which will be running on the Mobility First Click Router, it will try to send a query with the GUID it received from the previous element, and the Java server, GNRS server will be having a socket programming which will be which will be always in the listening mode. So once it receives the GUID, it tries to convert the GUID string received from the client. It tries to convert the whole string into bytes, and then it tries to make some hashing functions on the value in the bytes and try to produce some network addresses. Once a valid network address is obtained from the GNRS server side, the server socket program will try to send the obtained network addresses to the client, which has sent the query. So here try to this is the output I got from the client side and the server side. So now I have as at this point I am not able to, I have not yet connected the Java server I have, in the UDP socket I have created to the GNRS server, which is already built in the Java server. Because the GNRS has many functionalities which will be requiring to required to convert the GUID into a network address. So as for the future work, as for me, I'm trying to understand each and every method present in the GNRS server And once if I understand which functions I need to use and which functions can be utilized for the GUID to network address transformation, I'll try to integrate the socket program by calling those set of functions from the GNRS server. And once everything is set, the mobility first team can check the end-to-end functionality of the entire architecture. And I would like to thank my advisor, Professor Dr. Ray Chaudhary, for providing me such an opportunity to get an exposure in the current recent technologies such as mobility first architecture. And I'm very thankful to the WinLab team to providing me such an internship program.
Thank you. Do we have any questions? I guess not, and that actually brings us to the end of the internship. So I just want to say that this was quite an experience for all of us, given that this is in a fairly long history of FinLab internships. This was the first time that we didn't have our usual face-to-face meetings and participation of everybody in the same building. And I must admit that I was quite skeptical how this is going to end up, given that we are doing everything remotely. And I have to admit that I was completely wrong. It actually turned out to be quite successful. And so I want to thank you, everybody. And just to sort of say that I hope we will be able to meet in person sometime in the future, hopefully not too distant future. So thank you very much, everybody, and hope to see you next year.
Thank you.
Thank you very much. Thank you so much.
Thank you.
Thank you.
Bye-bye, guys.